podcast. We are two brothers who have been discussing and arguing about technology since we were kids and now decided to include you in these conversations.
Every week we will discuss some key developments in AI and how they will impact core AI technologies development and AI applications. Because AI will permeate everywhere and change everything, initially as a layer on top of existing systems, but then becoming itself the operating system of the world.
Today's episode is very special. We're looking at the return of analog computing. Yeah, we're taking you back in time, but it's modern stuff. Folks might be thinking when they're listening to this, are you going back in time really? No, we're not. We're actually talking about some cutting-edge science that has just been published in Nature Electronics. The paper, if you want to look for it, is titled Precise and Scalable Analog Matrix Equation Solving Using RRAM Chip.
Yeah, it's a bit of a mouthful, but trust us, it's a big deal. Before we even touch that paper, we need to get our fundamentals right. Because to really understand why it matters, you need to understand one thing. You need to understand the difference between training and inference in the world of artificial intelligence. In the world of artificial intelligence, there is two big concepts. There is training and inference. Training is actually when we create the models, and inference is when we use them, whether it is in production or in the testing phase. Think of AI training as building the brain. It's the phase where the model learns. It takes in huge amount of data, adjusts its internal parameters, and eventually understand patterns such as faces, voices, words, wherever you teach it.
And I guess people are listening to this and say, oh, that's amazing, but it's actually a tremendously brutal process. We're talking clusters of GPUs grinding away for days, weeks, even months. Training the big boys like GPT, Gemini cost tens or hundreds of millions. And that's just in terms of chips and energy when you have access to that. But that itself is becoming a short supply.
Exactly. But once trained, this model enters in a second life. It enters in the inference phase. That's where it starts thinking. That's where it starts to produce intelligence at last pretending to do it. Each time you prompt ChatGPT or your phone unlocks with your face, that's inference in action.
Yeah, so let's break it down for folks in terms of money. So the training phase is the expensive in terms of, but only if you look at it from a one-time expense. So you have to put a lot of money up front all at once to do the training. Now, inference might seem more like a operational expense. It's cheap per action, but when you add up all the billion of actions that are being processed, it also adds up to a lot of money. So in short, training is expensive, inference is expensive. Training needs a lot of money all at once. Inference needs a lot of money, but over a longer period of time. So it's all a lot of money.
Interestingly, inference, although it is cheaper per query, can become very expensive in total because of the huge amount of volume. Billions of users interacting will add up really fast. That's why everyone is obsessed with optimizing inference costs right now.
And that's actually the whole point of this discussion and this paper, which is the analog comeback. Because if you make these inferences faster, cheaper, and more efficient, suddenly you shifted the entire AI economy. And when you want to think about these inference, it's not just, doing some silly search on ChatGPT. It's AI becoming the layer that covers everything in our lives. When you're talking about robots, when you're talking about more optimized processes in industry, everything is going to be this layer of inference. So when we talk about faster, cheaper, more energy efficient, we're talking about the next industrial revolution being enabled with a new technology. So I think we can now actually talk about this paper and why it's so important. And that's something what we're trying to do in this podcast is really to give you the signal. There's a lot of noise happening in the AI field, and there is a lot of sort of notes being from one person to the other. So whatever the week's news, you'll hear it in every other podcast. But we're trying to bring you is something that everyone else is overlooking. So give you this signal, give you what's coming over the horizon in a format that you can understand. So we're bringing you into our conversation because that's what me and my brother have been talking about since forever, is really talking about where technology will go. So going back to this paper, Nature Electronics, precise and scalable analog matrix equation solving using RRAM chips. So on the surface, if you take a look at this paper, it's all about sort of the technology that goes into the 5G and the future G networks. It's called MIMO for multiple input, multiple output, and it's all about signal detection. But it's not really that, is it?
Yes, it's more about how can digital chips can be used in a new way, in a way that can be faster and cheaper than digital is what dominates modern computing right now. It processes information by counting with zeros and ones. It's very accurate, but very slow and consumes a lot of energy. On the other hand, analog chips think in flows. They think in physical parameters, physical voltages, currents, and charges that can take any value in between. Information is processed as a physical property.
It's a very poetic way to present things. But tell folks why we're talking about these analog chips. What's the history here? And what's changing with this new paper?
Historically, analog chips were mostly seen as exotic, cool for demos, but not scalable. This paper breaks this myth. It shows analog chips performing matrix inversion, a key operation in second-order AI training algorithms, something that was not been able to do before.
So when we're saying these sort of matrix inversions, second-order training algorithm, sort of in simple language, what are we talking about?
AI training involves a lot of math, heavy linear algebra, where matrix operations like multiplication and inversion are core. GPU are great for this, but now we do have analog chips, and they can do the same thing in a lot more faster and a lot more efficient way.
Okay, so basically, if they can do the core stuff in AI, we started out saying it's inference, but it's not really inference. Now we can even do training, isn't it?
Yes, previously analog chips were thought to be able to do inference better than digital chips. But here it has been shown that something like matrix inversion can be done using analog chips. The authors demonstrate that their analog system could implement matrix inversion, which is central to second-order optimization. That's a class of algorithm that use curvative information or second-order derivative to make training more efficient.
And so what would that mean for the AI in practice? It's not just basically the last step of recognizing a cat after you have the training. It's really now we're talking about using analog chip to optimize the rate of learning and making it smarter and faster, isn't it?
Yeah, we already knew that analog chips could be used for inference, but this paper shows that it can be also used for training. As we already previously said, the inference step is not capital intensive, but operationally very expensive. It needs to be optimized, but analog chips, in order to be used for inference, the engineers need to solve a lot of problems related to creating analog chips. They need to scale the manufacturing. But if we use those analog chips in training, this is a whole different situation where although we do not have the actual scaling of manufacturing, it becomes these analog chips become really valuable tool for the AI engineers. Okay, and the heart of it is what we call analog matrix computing (AMC) system. Each tiny RRAM cell stores a conductance of value, basically a number represented as a resistance.
So really the key for this technology, and what's amazing about it is that really the physics itself becomes the matrix of multiplication. It's capturing all these properties and all these operations in the very physics of the chip, isn't it?
Yes. You do not simulate the map with the math in the analog chips. You do not simulate the map. The circuit is the map, and furthermore, you do the operation right within the memory. There is no separate unit in GPUs. We do know that there is VRAM, where the actual model is stored, and there is the tensor core where the operation is done. And the chip and the GPU need to flow information from the VRAM to the tensor core, where the operation done in the tensor core and they're stored in the VRAM. But here with the analog chips, everything is done right within the memory, within the actual physical, not simulation. No simulation. The circuit is the math actually.
So anyone listening to this is, analog has been around for a long time. Why hasn't it been used? Why are these two brothers just telling me about this stuff? And the answer is, for a long time, it was dismissed as a very noisy system, but this paper shows differently, isn't it?
Yes, they solved a very important issue with the analog chip. They solved the precision issue. That's what's revolutionary. They solved the 16 by 16 matrix equation at a 4-bit precision. To get there, they used a technique called bit slicing, stacking multiple 3-bit RR layers to emulate floating point operations.
So basically, this is like the hardware version of a floating point math. But all of this is done at a speed of a moving electron through matter. So it accelerates the whole process tremendously.
Yes, exactly. And all of this is without a CPU in the loop. It's all done within the AM memory.
Yeah, it's just incredible stuff. And a lot of times, when you read the paper, and kind of like the tech criticism of this is just science. It's done in a lab, but this is not. This is why we're interested, because again, we don't want to talk about sort of something that's 30 years from now. We're talking about stuff that we believe could impact our lives and technology in the years to come. And so in this paper, what they did is they actually applied it and tested it in something practical. So these multiple input, multiple output, these multi-antenna systems used in 5G stations. And what this technology enabled is to have hundreds of antennas all talking at once. So there's a practical application of this stuff.
Yes, in this MIMO, massive multi-antenna system, the challenge is separating all those signals, solving huge matrix equations fast and with huge precision. Their analog solver did this using the zero forcing detection method, reaching performance comparable to F32 digital precision in just 3 iterations due to use of analog chips, you know?
Yeah, so in practical terms, for people who are not physics, who don't have a physics background, we're talking about a 1000x improvement in speed and 100x improvement in energy efficiency. So we're not talking about some Moore's law or some incremental improvement. We're talking about leaps, the kind of stuff you can only do by leveraging physics. So it's very impressive technology.
Exactly. And while this was applied to communication, the same math, solving AX equal B, underpins almost everything in signal processing, scientific computing, and crucially in AI training.
So this is why we're sharing with you this technology, is that when you think of AI, when you think of tech, you want to be open-minded of what's happening in the world of technology. And what we really love about this work is it shows that analog never really died. And when you think about the world, the digital world is a kind of a poor representation of things, whereas the analog is a perfect representation of the world. When you think about sound, when you think about light, motion, temperature, it's all analog, whereas digital is just on and off switches. That's a very poor representation
of reality. Even the digital CPU rely on some kind of analog components like amplifiers or oscillators and converters. That's there's where there is always this little analog heart beating under all this binary, and that heart is still handcrafted. Analog design isn't coded, it's composed. Engineers literally shape the flow of electron with intuition and a sense of
Yeah, when you say these things, it reminds me a little bit of a jazz band that's going on stage and they just know each other, they know what they want to play, and they don't really calculate the notes, they just feel it. And that's why analog design has resisted full automation, because you can't really fully abstract physics.
Yeah, but the thing is, now we do have AI, so this art itself might be automated, and this analog intuition, it can be automated with AI, bridging the human and the physical, a full circle moment, you know?
Yeah, it's great. It's interesting because basically the chip, I mean, a lot of people when they talk about AI, they talk about how at some point, AI will improve the development of AI chips, and you'll get that cycle. But I think in many ways the analog chips are going to be the one that benefit the most and that push this cycle the furthest.
Well, the design of digital AI chip is already using a lot of AI. Where the Jensen Huang, the CEO of NVIDIA, said that without AI, the NVIDIA cannot design its own chip. By the way, it's already very very important for design of a digital chip. But right now, with all these this discovery, with papers like this, we are realizing that this AI can also be used to design better, in a more scalable way, analog chips.
Yeah, the only question becomes now, given the size of the GPU market and the dominant position, and in many ways, the manufacturing is the challenge for these technologies. Can analog compete in terms of volume? But I guess if it's 1,000 times faster and 1,000 and 100 times energy and efficient, it could compete if it can produce sufficient.
But also we need to talk about RRAM memory. RRAM memory. Those are resistive random access memory. That's at the heart of this analog chip. RRAM memory is basically a MIM resistor based memory. Each connection changes resistance when voltage is applied, and it remembers the state. You can think of it as a storage and the computation fused together. This is amazing, and this is something that had not been seen in the entire world.